included. But again, if the final expression agrees with experiment, then it's adequate. If you include those termination steps, then if you include one of those termination steps and not the other, then you have to see what assumptions you have to make about the rate constant for those termination steps in order to agree with experiment. Other questions? Okay. Well, if you remember what we were doing for the last week or so, is we were using a batch reactor, that is a time-dependent reactor with no inlet and no outlet, in order to try to determine for a given chemistry that our chemist friends gave us. We were trying to determine an adequate rate expression. Why do I say an adequate rate expression rather than the rate expression? Let's see, we started the first row, the last row, why don't we start the second row today? There could be many that work. There's no guarantee that one that we find is the only one. But we want to find the mechanism, and the mechanism also, by the way, what is a mechanism? What do we say? What do we mean when we say mechanism?
It's a chain of reaction between which leads to the other reaction.
I would use the word a set. A chain usually has a different meaning, but a set of elementary reactions. And what is an elementary reaction? What do we think of as an elementary reaction? What does that mean?
It's a reaction that doesn't require.
This reaction doesn't require multiple steps, but what are we guessing? What do we believe?
Where the stoichiometry of the reaction is equals
I'm not sure what that means.
where I say that A plus B is equal to R. So the stoichiometry
There are no intermediate reactions. There are no intermediate products being destroyed.
No intermediate steps. What are you trying to say here?
That the rate equation follows the way that the chemical reaction equation looks.
That we're the guess, and it's not when we guess that something is elementary. We don't know for sure. When we guess that it's elementary, we're presuming that what we write down is actually what's going on a molecular basis. We don't know that, and the only way we can test that is if the kinetics look like that of something that's actually going on. In other words, if we write A plus B goes to product, we're picturing an A molecule and a B molecule banging into each other and reacting. If there were more steps in between, then it wouldn't be that simple. The A and the B's would be doing lots of other things. But if we believe that A plus B goes to R as an elementary reaction, we're saying that we're guessing that what's going on in that reaction is A and B are banging into each other and then coming out with R, and that there aren't any middle steps. We don't know that that's the case, but that's a guess when we guess that something's an elementary reaction. Okay, well, we have dual goals, or goals that come together. One is for a chemistry, set of chemical reactions that our chemist friends give us, we would like to come up with an adequate mechanism. Adequate meaning that when we write down the equations and we solve them, they agree with the experiment. They give us the right shapes. But more than that, these mechanisms always have rate constants, unknown parameters, these Ks. And we'd also like to, from experiment, determine those Ks. So those are the goals. And until now, we've spoken about batch reactors. And there are two general classes of reactors that we could work with. There's batch, and there's flow. In a batch reactor, that's what we've been dealing with so far. Before we start the reaction, we fill up the reactor, and then we close the inlet and the outlet. And at T is equal to 0, we flip a switch, whatever that means, and we let the system evolve in time. So the concentration depends on time. Concentrations depend on time. in a flow reactor, but there's no inlet and no outlet. In a flow reactor, what we have is we have a reactor where for all times stuff is coming in and coming out. But if we have steady state, and there's no guarantee that we will, if we achieve steady state, then we get to a situation where the concentrations are no longer functions of time. And both of these are tools both of these allow us to investigate reactions. Now, when would we use a batch reactor and when would we use a flow reactor? What are the advantages? Well, with a batch reactor, we need very little auxiliary equipment. Since there's no inlet and outlet that are operating, you don't need any pumps, active pumps. We just stick everything in and we let it go. On the other hand, the flow reactor, you need pumps, and typically it's a more complicated system as far as mechanically. The other thing is, a batch reactor, you can run one reaction in it, and then when you're done, you clean out, you run another reaction. Usually it's not too hard to turn it off because the reaction's over. In a flow reactor, usually you have all this equipment that's running, and in principle it could run for a long time. So you have to stop, and it's a bigger deal to change over from one reaction to another. However, the nice thing is, if things change very quickly, if you have reactions that are very fast, sometimes it's very hard to accurately measure everything if things are changing very quickly here. So you need methods to do quick measurements. Whereas over here, if you can reach steady state, things aren't changing with time. In fact, if things don't change with time, what do they change with? Typically, we might measure what's going on here or here. In the reactor and the outlet, we might measure what's going on. So the observers, what are they going to be a function of at steady state if they're not a function of time?
Position.
Well, possibly position. What else could they be a function of?
State properties.
Flow rate. They could be a function of the flow rate and the composition of what I put in here. So the independent variables, independent means the ones that you manipulate, might be position, it could be flow rate, or something equivalent to that, the volume of the reactor, but you're not going to really change that. And also the composition of the feed. And those are all things, and what do you observe? You observe the concentration at the outlet and the concentration as a function of position in the reactor. Those are things that you can deal with. And, yeah, okay. And when I do my analysis, when I do my analysis, I can use two methods to do my analysis. So these are the reactor types. And if I do my analysis, well, let's think for a minute. When we did our analysis of the batch reactor, we wrote out a mechanism, and then we wrote out the corresponding differential equations. And then what we did is we tried to somehow solve the differential equation. Remember, in your homework, try to solve, that meant that you had one species, say A, the reactant, and you tried to come up with an expression for the rate of reaction with respect to A. In terms of concentrations you could measure, you tried to get rid of the concentrations of the reactive intermediates. But the end product of your analysis was the rate of A, 1 over V, V and A, V. Remember? Homework? Okay, so that's called the differential analysis. That is, you have a set of differential equations, and you manipulate them, but in the end you still have a derivative, a time derivative. And then you try to measure the time derivative in the experiment. You measure the rates. And if you remember, we spoke about various situations. We spoke about the method of excesses, instead of the method of stoichiometric ratios. All of those we spoke about in the context of trying to measure the rate. Remember, we did it with initial slopes. We were measuring slopes. So we were measuring derivatives. So in the differential analysis, you have equations that look like RA or B, etc. You might manipulate the right-hand sides of these equations, but you measure derivatives and you compare. You compare the measured derivatives. Now, how do you measure a derivative? You measure 2 or 3 points and you calculate the slope. So now, the good thing about this is it's pretty direct. That is, you kind of see exactly what you're doing. You have a rate expression that you got from your mechanism, and you measure something that you convert into derivatives and you compare. The problem with that is, one problem, is that often it's hard to get an accurate measurement of derivatives. And you can illustrate that with a picture. If we draw a little picture here, let's say this is my true function. It's a straight line. And let's say I'm doing an experiment. And the experiment has a little bit of error. So I have one point that's a little bit high, and another point that's a little bit low. And they're not, one is not a lot high, and the other one is not a lot low. But you can imagine, let's say I tried to take the derivative by taking delta y, delta x. If I did, I would get this curve. And you can see that even though the data points are pretty close to the true line, the slope is very different. And this is an illustration of how taking numerical derivatives is called a noise amplifying process. It's noise, a little bit of noise in the function gives you a lot bigger noise in the derivative. So what that means is, not that you should never use the differential analysis. In fact, today, most people use the differential analysis. However, it means that you need very, very, very accurate data. If your measurement technique or your data is not super accurate, then the differential analysis is going to give you big errors. So what's the other idea, the other possibility? Well, notice what I did here. The theory gave me derivatives. The experiment gave me x's, which I then converted to derivatives. So what I did is I took theory that has derivatives, data that has points, and then I took derivatives of the data to compare with the theory. What's another way of doing it?
Integration.
Integration of what? Volunteer? Right, instead of differentiating data to compare, why don't I integrate the theory to compare? If differentiation is a noise amplifying process, integration is a noise smoothing process. Now, before we do that, let's just notice that noise smoothing is not always the best thing in the world either. And we're going to do it because sometimes you may have two theories that are pretty similar. And if you smooth too much, you're going to smooth out the difference between the theories. So integration is also not always the appropriate thing. But we're going to look at the integral method. And the integral method of analysis, again, you've got your mechanism. Here I also had a mechanism that gave us these. Gave me RA, RB. And we had to measure the concentrations. And instead of taking derivatives here, we integrate this. How should I write this? It's from here. Integrate to get C of t, or C of whatever, and then we compare. We're over here, to be more precise, we measured C and we calculated derivatives. So So here we compare derivatives, here we compare concentrations. So that's the difference. And let's see how we can do that. All right. So anything else I want to say before going on and doing that? Last thing. Okay. So go out of order and say something about this? No. I'll get back to that later. Okay. So let's see how we use the integral analysis in the batch reaction. Until now, we've only done the batch reactor with the differential analysis. That's why I gave you all those homeworks, and that's why I wanted them to be done by today, so we could be all experts on the differential analysis in the batch reactor. So now we can do the integral method. All right, so how do we do that? Well, remember, what was our basic equation of kinetics that was analogous to Newton's second law? What was I up to?
The force equals the time derivative of momentum.
That was, yeah, and what was the analogy in reaction kinetics?
I don't remember.
That's because you didn't look at your notes. Next. Okay, remember, as soon as I get 4 people in a row who don't know, who haven't looked at the notes, we have a quiz. That's the way it's going to work. Got that? So that way everyone can blame you and the next 3 people. What is that's 2. I'm getting close to quiz time. No, I can't. That's a stalling tactic.
You had RA as a function of concentration and temperature is equal to the sum of K function of T times.
No. I can't hear you. 1 over V between A dt is equal to RA. That was pretty close to a quiz. If you're not even if you're not motivated to look at your notes, just think of how much your classmates will love you if you're the one who causes everyone to take the quiz. That should be motivation to look at your notes, because some of the other people in the class might not be very nice if you make them take the quiz. Okay, so this is the expression. So let's see how and remember, just as in Newton's second law, we need, for any particular, this always holds, but for a particular problem, you need a constitutive equation for the force. Here, this always holds. You just, for any particular problem, you need a constitutive equation for RA that depends on the mechanism. And we spoke about that. So, but in general, how would the integral method of analysis work? If I want to integrate this, I need to separate variables. And RA, typically, well, let's write it out first. So typically I would try to separate variables, dNA over V RA is equal to dt, which then I would integrate from 0 to t